In this active circuit, prove that V out is 13 times V in. Let's make the assumption that op amps are properly biased, so the positive negative supply voltages are connected correctly, and as you can see, we have negative feedback for both op amp in this circuit. So with that in mind, we make the assumption op amps are linear region of operation not saturated, and therefore virtual short for them is valid. By that I mean virtual short is valid for both of them, which means the positive input terminal voltage is equal to the negative input terminal voltage for each op amp. Now, if V out is showing up here, you can see that immediately right after that we have this this voltage division between the resistors, and there is no current that is flowing through the input terminal of ideal op amp because it has infinite impedance. Therefore, if we have V out at this node, half of it should show up here. So we have V out over 2. Now, because of the virtual short that I talked about, because V out over 2 is now at positive input terminal of op amp, it should also appear at negative terminal. So here should be V out over 2 as well. Now you can see that there is no current flowing through the input terminal of our ideal op amp. Therefore, as a result of that, we get, let me change the color so that you can see it easily. As a result of that, you get the current that is flowing this way should continue and going downward through this resistor. So if we have V out over 2 halfway, then we should have V out here on top. Another way to take a look at it is think about this second op amp in the formation of non-inverting amplifier. On the positive input terminal, you have V out over 2. So here we have V out over 2. Negative input terminal, as you can see, we have a resistor here, which is this resistor. And we have a resistor here grounded, which is this resistor. And this is obvious non-inverting formation, and for that we have output is simply 1 plus feedback resistor divided by the other resistor times input, which is V out over 2. This is gain of 2, so 2 times V out over 2 give us V out, which is exactly what I wrote here. So we have V out here. Now let's go to the first op amp. In the first op amp, as you can see, again, it's in linear region, not saturated, and ideal. So if V in is at positive input terminal, because of virtual short, we should have V in also at negative input terminal. Great. Now, there is no current that can flow through the input input terminal of ideal op amp because it has infinite impedance. Therefore, there is no voltage drop across this resistor. As a result, if we have V in here, that V in should appear here as well. Great. Okay, so let's name these nodes also as A and B. We need to find VA and VB. So what is this current I that is flowing from V in from this node downward? So that current I is simply V in divided by resistor R. Let's keep that. That current I should also flow this way because it cannot go through further left because it cannot go to the input terminal of op amp. So as a result of that, VA is simply I times 2R, which means it's 2 times VN. Great. So we found VA. Now there is this current I flowing from node A down to the left side. Now what is this current that is going downward? Let's name it current I2. So what is I2? Well, I2 is simply VA divided by the resistor R. So, and VA is 2 times VN divided by resistor R. So obviously, considering equation 1, so from equation 1, you can see that it's 2 times I, because VN over R is I. Great. So we found I2 2 times I. As a result, if you write a KCL at node A, so I'm going to write it here, KCL at node A, that state that the current that is coming to node A should be the sum of I2 and I. So that I2 is 2I, so therefore this is 3I that is coming from B to A. So we have 3I, so therefore I plus I2 is 3I. Okay, now we want to find voltage at node B, so let's find it. Voltage at node B is the 3I that we found that is going through, so I'm going to write it. the 3 times I that we found that goes through the resistor R on top. Let me change the color so that you can see it. By that I mean this. So 3 times I is going through this resistor R, and it results in voltage drop, that is 3I times R, and then plus VA. Okay, so what do we get then? VB is 3 times IR, which is 3 times VN, and VA is 2 times VN. Alright, so we got VB is equal to 5 times VN. Okay, that's very good. So we found VB, and finally 3 times I is going from node B to the left side. What is the current that is going downward from node B? Let's name it I3. So I3 is VB divided by the resistor that is going through it, R. VB is 5 times VN, we just found it, divided by R, which means 5 times I, because VN over R from equation 1 is 5 times I. Great. So what it means, 5 times I, which is I3, is going downward from node B, and 3 times I going left. So because of KCL at node B, it means that 3I plus 5I give you 8I that goes from the V out to VB. So therefore, finally, what is V out? V out is equal to the 8 times I that is going through resistor R plus VB. So it becomes 8 times IR plus voltage at node B, which we just found it to be 5 VN. Great. Okay, but VN from equation 1, VN is IR. So this is VN. So we have 8 VN plus 5 VN. And this means we have 13 VN. And that's exactly what we wanted to get to for V out. So basically combination of a number of KCL we wrote for nodes A, B, and then utilizing the KVL in terms of adding the voltage drop across resistors and voltages helped us to get to what we wanted, which is proving V out is equal to 13 times V in.